Hello everyone, in this video I'm going to show you how to use a mesh in Abaqus. The objectives are what is mesh, understanding the role of the mesh module, assigning an Abaqus element type, and understanding a mesh generation. So what is mesh? One of the most crucial processes in carrying out an effective simulation using the FEA is meshing. A mesh is composed of elements that have nodes, coordinate position in space that might change depending on an element type that represent the geometry's shape. A final element software cannot cope with the unusual form easily, but is much more comfortable with the standard shapes such as cubes. The act of transferring these irregular shape into a more identifiable volume known as element is known as meshing. So when we say irregular form, is look at this geometry. So this is, for instance, a single lap joint. That we have a component at the top, we have another component at the bottom, and we have a adhesive in the middle. Okay. So if you want to do a finite element analysis on this one, it would be very difficult for Abaqus to solve a mathematical equation for a geometry like this, and probably you will get an error. Therefore, we would Abaqus prefer to transfer this geometry to the smaller area that we call them elements. So if I go to mesh, you will see that we transfer this geometry to the smaller element that is Q. Which would be much easier for a solver to solve this mathematical equation for these elements. So as you can see, this is, for instance, a 2D element that has 4 nodes. And Abaqus will solve this mathematical equation for each of these nodes. So the next question is, why is a good quality mesh important? A poor quality mesh causes a convergence issue, resulting in inaccurate founding and misleading conclusion. The quality of the mesh depending on a few scenarios. First, what type of analysis you are doing? Is this something that you want to get a rough idea about stress, or is it something that you want to make a decision based on a stress analysis? How much time you want to invest in the meshing, because you could have a very complex geometry and sometimes you have to spend a lot of time partitioning your part to have an absolutely perfect mesh. And how much time you want to invest in solving. This is another question, because the finer mesh, the higher it's going to be the CPU time. So there should be a balance between the quality of the mesh and the solving time. And that's very important, and that's a skill that you gradually gain using the FEA software. For instance, this is an example that you see there. We have a hook here. So there are two types of mesh. So you have a coarse mesh here, and we have a fine mesh on the other side. And obviously, this it would be much quicker to solve the coarse mesh, but you might not get a very accurate result. So that's why we have something that we call it mesh study, that later you're going to learn about that as well. So in Abaqus, we have the mesh module, similar to the other module that you learned. We have some new tools at the top, and the bottom region are the same as the one that you had, for instance, in part. You see that you have all these sections going to be the same in the mesh section. So from the top, I'm going to go to wireframe first. By the way, you can download these file from a resources section. So I have this 2D truss, and I want to apply a mesh on this one. So what we have here, we have here we have seed part that we basically apply a node, and then we have seed edge that we apply the number of the elements, or the size of the elements on an edge or surface. Then here we have mesh part that we will basically assign that to our geometry, similar to what we have in the property. If you remember, we were creating our material, we were creating a section, we were assigning that to the geometry. We have exactly the same thing here. We're either going to use this one, or we're going to use this one, and we assign it to mesh part. Then we have mesh control that we basically here we have the type of the mesh that we're going to apply, and then we have a mesh orientation, and then element type. That gradually in this video you're going to learn about all of these. Okay, so before I start teaching you these things, there's going to be something related to what you learn in assembly section. If you remember, in assembly section, when you wanted to import your part, you had two options at the bottom here. So you had dependent and you had independent. So this is just a catch-up from the assembly section. And a dependent instance is only a pointer to the original part. And in contrast, independent part instance is a copy of the geometry of the original part. Okay. This is important because the way I import my part into assembly will affect a mesh. So as you can see here, it's a dependent mesh on a part, independent mesh on instance. And if you look at the mesh section, you'll see that at the top here, we have object, we have assembly, and we have part. So if we select the dependent, then mesh should be on a part, so I have to go on a part. And if I select independent, then mesh should be on instance. So in order for you to understand this better, I suggest you to remove this one, and I delete this one. So now I'm not on the wireframe. So I'm going to go to wireframe, delete this one, and I import a new one. So first one, I'll select the mesh on a part and say OK, and then I'm going to go to mesh. And if I try to apply a mesh, you'll see that I get an error. It says dependent part insert cannot be edited or assigned mesh attributes. Okay, but if I go to part, you'll see that if I click on this command, then it's active, so I can apply a approximate global size. And another point is that you'll see that at the bottom here, underneath of the part, something will appear called mesh. The currently is empty, so you don't have anything. Okay. So now again, let's remove this one. This time, import it as a instance. So now I'm going to import it as an independent instance. Click on OK. And then again, if I go to mesh, you'll see that this time I can import it in an assembly. However, if I go to part, I won't be able to import it. Okay, so this is important. And also, you'll see that we don't have a mesh there anymore, and the mesh will appear in the assembly section. So this is very important. So you have the way that you import your part in assembly will affect the mesh. So it doesn't really matter the way that you want to import it. Just make sure that if you got an error, then you have to select the other one because you imported it, for instance, as a dependent. So what I want to do now, I want to apply a mesh to this truss. And there are two ways of doing this. The first one is if I want to apply a same size mesh everywhere on this truss, then I will use the seed part instance. And then I can apply a global size. For instance, this is 13. I can reduce this one, let's say 10. And once I play on apply, you'll see that I can see the nodes on the parts. And when I'm happy with that, I'll click on OK. And the next step is to apply this to the geometry. Then what I would do, I would click on mesh part instance and select the geometry, because we have one geometry, so it's already selected, and click on yes. And as you can see, it turned blue. That means that I have applied the mesh. We have the same thing in property. If you remember, create a section and apply that. And the color is important. So when it turned blue, that means that we have the mesh on our geometry. However, because this is 2D and wire, we won't be able to see it. One of the way of seeing this one is to go to assembly display option, and if you go to the mesh at the top, you can activate the show element label, click on apply, and you can see the element number on each element. Okay, so that's one way of applying a mesh. Now I can cancel this one. If I'm not happy with it, I can just delete the instance by clicking on the corner, select this one, and the geometry is already selected, and click on yes. And it will ask me, are you sure you want to remove it? And I said yes, so I don't have a mesh anymore. The next one is that if I want to apply a different size mesh on some specific area, then I have to use this seed edge. And let's say if I select the these lines at the top. Click on OK, and I apply, for instance, 10 millimeter, and click on apply. Also, in this section, we have something new that is basically by number. So you have an option to apply this by size. For instance, this is like I'm using a SI millimeter, so it's going to be 10 millimeter. I also have an option to apply this by number, so I can give the number of the element that I want on that specific area. On the other side, we have something called the seed constraint. So the default normally is the top one. So it will. This is a default setting. The number of the element along an edge can either increase or decrease, so that the mesh can become denser or coarser, that is specified by a seed. The middle one will only allow the mesh to increase, not decrease. So the number of the element along the edge may be increased during a mesh generation, but cannot be decreased. And the last one is fully constrained, and you say that you are not allowed to increase or decrease the mesh, and just apply what I tell you. For instance, if it's 10 millimeter. And the last one, if you have a complex geometry, you would definitely have a problem. So I wouldn't recommend you to choose the last one. So the best one is this one. So you don't want to allow a software to decrease the number of the mesh, but you are happy to increase the number of the mesh a little bit. So I always keep this one in the middle. Okay, so now I'm applying this one, click on OK. Then for these two lines at the bottom, I'm going to apply a different mesh size. So I'm going to hold this one, click on OK, and instead I will apply, for instance, 5 millimeter, click on apply, and click on OK. So as you can see, I have more elements at the bottom, and if I apply this one, click on yes, you'll see that I have more elements in the at the bottom line in comparison to the top line. We use this technique because in real life, when we do FEA analysis, some part of the geometry is more interesting. You have a higher stress concentration in those areas, so you will want more accurate result in those areas. And some areas are not really important, so you apply a coarse mesh. So this one will give you that flexibility to increase or decrease the mesh size on a specific area. In the next step in Abaqus, I want to show you bias seeding. Basically in bias seeding, what you can do, you can apply a finer mesh in one edge or on one side and coarse mesh on the other side, or too fine on two sides and coarse mesh in the middle. So in order to practice this one, go to composite, not composite, go to bias seeding. So we have this plate, and if I go to mesh section, and this time because this is dependent, so I'll go to part, and what I want to do, I want to apply a mesh on this one. So let's select the seed edge and select this one, this edge, hold the shift and select the other seed and click on OK. And what I'm going to do, I'm going to apply 5. This is a little bit too fine, so I'll just make this one, let's say 10. Apply. So this is just a basic normal seeding. But if I select on a bias single and then click on apply, you'll see that I have the minimum size 1 and maximum size 5. So on this edge, I have 5 millimeter as the element, and the element size will reduce gradually until I have on the other side 1 millimeter. And it's the same thing with the other one. And if I want to change the direction, I will just click on this one, select, and you click on done, and you see that the direction will change, and you click on apply. Okay, so I can click on OK, and you'll see that I have a finer mesh in this edge and coarse mesh on the other side. And I can do exactly the same to the other one. So if I click on this one and click on this one and click on done, but this time I'm going to use double. So if I say apply, you'll see that I have a finer mesh in the edges and the corner, coarse in the middle. You also can flip this one, so you can click on this and OK. So if you apply this, you'll have finer mesh in the middle and coarse mesh at the top. But I want the fine mesh to be at the edges, so click on apply and OK. I'm gonna assign this mesh, and if I say yes, so we can just deactivate this element's name. You'll see that I have very fine mesh in this corner, and a coarse mesh in the middle. So when I do analysis, that means that I'm more interested about information in this area, because I actually know that there is a higher stress concentration on those areas. So these are the tools that Abaqus will give you, so you can apply a finer mesh on a specific point. Now I'm going to show you how to assign a mesh control in Abaqus. If you click on assign mesh control, you'll see that here at the top we have element shape, we have a technique and algorithm that gradually I'm going to explain these in this video. So in 2D, what we have here is called a quad. It use exclusively quadrilateral elements. So as you can see, these type of element that you would have. Just make it bigger so it will be easier to see. And then we have quad dominated, use primarily quadrilateral element but allow a triangle in a transition area. So although majority of them is quadrilateral, but in some area, for instance, as you can see in this region, we will have triangle as well. And the last one is this setting is the only available when you apply a mesh control to a face of the solid region, since the triangle face mesh will be used to generate a tetrahedral solid mesh. So as you can see, this is a type of the mesh you would have using a tri element. So let's try this one. So if I so currently the mesh that I apply to this one is a quad mesh. And if I go to try and keep this one as free, click on OK, and it will ask me if I should remove the mesh. I'll say yes, remove it. And as you can see, everything has changed here. And if I say assign the mesh, click on yes, you'll see that I have the triangles instead of a quadrilateral mesh. So basically what we do here, we basically define the element shape that we have. The Abaqus has a different element shape that I'll show you in a second, the type of the element that we have in Abaqus. So you see that we have a one-dimensional, so it's going to be only line that you learned in the previous example. And then we have two-dimensional, it's a triangle or quadrilateral. And then we have a three-dimensional. In order to see the three-dimensional from here, I suggest you to go to mesh control. So we'll have a solid example here. So again, if you click on mesh control, so here you will see that I have hex dominated, tet, and wedge. Okay, so these one are a little bit different than the 2D ones. So hex exclusively use a hexahedral element. Hex dominated use a primary hexahedral element, but allows some triangle as well. So as you can see, we have some triangle in the mesh here. Tet use exclusively a tetrahedral element, and wedge use exclusively wedge element. So the type element shape, it really depends on depends on your geometry basically. If you have 3D, you will have hex dominated tet, and if you have 2D, then you would have quad dominated and tri. And the element shape in Abaqus also we have, as you can see here, these are a typical element shape that we have in Abaqus. So as you can see here in Abaqus, the number of the node that we have, for instance, in one dimension we have 2 nodes, and in a line we can also have 3 nodes. So there's going to be another element, another node between the 2 nodes, and then I'm going to explain this later, how you can have or you can deactivate this node in Abaqus. And obviously having more nodes will give you a more accurate result. So imagine if you have this curve and you don't have this node in the middle. So what will happen basically, your curvature is not going to be the smooth curvature. So you're going to have like a kind of like a curvature, but it's not smooth, so the accuracy of the result will reduce. Similar to this one. So as you can see, if I have a curvature here, I definitely need the point in the middle. And if I don't have that point, then that will transfer to a straight line. So it's important to have, depends on the geometry, sometimes it's important to have a node between two nodes. But generally, the default in triangle, in 2D, you have 3 nodes. In quadrilateral, you will have 4 nodes. In line, you have 2. And if you're using a 3-dimensional, and if it's a triangle, you have 4. And if it's a hexahedral, then you will have 8. Okay, so you have to be careful about this because of the license that we have as an education license. So the education license is limited to the number of the element that you have. So those, or number of the node basically, and currently I think it's on 1000. So the 1000, that means that you cannot have more than 1000 node in your geometry. So normally the software companies, they would restrict their software based on the elements or the node number, and the more you pay, the more a node will be available for you to have more complex geometry basically. Okay. Now in the next step, I'm going to show you the technique that we have in a mesh control. So as you can see here, we have free, structure, and sweep. Okay, and so let's just start from these two. So we have free and structure. So structure is very obvious that we call it structure mesh, and the free is the type of mesh we call it unstructured mesh. The structure mesh are a mesh with the implicit connectivity whose structure allows for an easy identification of the element and nodes. And unstructured meshes are a mesh with a general connectivity whose structure is arbitrary. So as you can see, the difference between a structure and unstructured mesh in these two pictures. Now the question is that which one is the best? And the answer is that it really depends on your geometry. Structured mesh are memory efficient, fast to solve, and unstructured mesh are good for complex geometry and arbitrary position. So my recommendation is that if you can apply a structure mesh, then you should, because it's faster to solve and easy to change it. But in some cases, when you have extremely complex geometry, then it would be very, very complex to apply a structure mesh, and that means that you have to spend a lot of time to apply a structure mesh. And that's why in the second slide I showed you here is the question is how much time you want to invest in the mesh. This is a very important question, because do you want to spend, I don't know, hours to create an absolutely perfect mesh? Well, the time that you're going to save on a CPU time is not going to be significant. So before actually solving any problem in a finite element software, you have to think about these things. If your geometry is simple, yeah, we're going to go for a structure or sweep mesh. And if the geometry is complex, is it worth to spend enough time to create a structure mesh? Are we going to save a lot of time on a CPU time? So these are the questions you should ask before submitting your job and run your simulation. The third one, we have sweep. And the sweep mesh technique involves 2 phases. It creates a mesh on one side of the region known as a source side, and copies the node of that mesh one element layer at a time until the final side known as a target side is reached. So as you can see, this is the example. So software will apply a mesh on the source side that we have here, and then the nodes will be copied until we reach to the other side. Okay. So now to have more example, I will ask you to go to structure mesh. And if you go to assembly, you'll see that we have 2 plates here. Okay, one simple plate and one we have a hole inside. Okay, and if I click on mesh, you'll see that here. If I click on mesh control, and select both of them, click on done, and select, for instance, quad, you'll see I have free and I have structured. Okay. And if I want to tell software, you know what, I want to apply a structure mesh on both of these, and if I click on structure, you'll see that I get the error, and software says the region highlighted in purple are too complex for a structure meshing. Okay, to remove from the current list of the selected region, and I'll say okay, fine, and click on OK. And as you can see, this one turned green and this one didn't turn green because it was too complex for Abaqus to apply a structure mesh on this one. So then, in the next step, I will apply seed edges on this one, and I will say this is, for instance, let's say 5mm. Click on OK. Click on OK, and select both faces. Click on done. And as you can see, we have very structured mesh here, or rectangle. On the other side, we have very arbitrary shapes, basically. And so what was the reason that Abaqus didn't mesh this one? In order to apply a structure mesh, you have to follow some rules in Abaqus. The structure mesh can be used in the 2D geometry if the region has no holes, isolated edges, or isolated vertices. The region is bounded by 3 to 5 logical sides, where each side is connected set of edges. And as you can see, these are example of basically structured mesh. But this is not the end of the board. We still can apply a structure mesh to this one if we want. And in order to do that, we have to simplify the geometry for Abaqus. So we will be able to apply a structure mesh. And one of the way of simplifying structure for Abaqus is to apply a partition. And there are different ways of applying the partition. So as you can see here, I just gave you 3 different examples. And which one is correct? It really depends on the application and the way that you apply force and what actually you're looking for. So these are the questions that you need to ask yourself before applying a mesh. For instance, as you can see here, in this one, we have very dense mesh in the middle. So these are perfect if you have a high stress concentration around the hole. So this type of mesh is really good. And this one, on the other hand, as you can see, I have a very basic, good quality mesh. So, as I said, it really depends on application. So now let's practice this partitioning on this 2D face. So I want to apply this, the middle one. So I have to go to part, and from the top, select the part 2. And for a face 2D plate partitioning, I have to select on partition face, and I can simply select this line from here to here. And I cancel this one, I'll select from here to here, and then I click on OK. So as you can see, I have this partition here. Then if I go to mesh and go to assembly, then I can assign a mesh to this one, and I say I want it structure, and then click on OK. Then as you can see, I have a structure mesh here. Because it turned green, so it's possible to apply a structure mesh. Partitioning your part will give you more flexibility as well. Because in the previous one, if you want to increase the number of the element around that point, you would only have that edge. However, by applying a partition, you also have access to these edges as well. So let's say if I want to apply a mesh on this one, so I'll say that this is 5 everywhere. Then I want to actually reduce element size on these one. So what I will do, I will first select these edges. I select this one, this one, this one, this one. And then let's say I will make this one 2. And then for this, I'll select this one and this one, and this one, click on done, and select on single, apply, selected that one too, so this one too as well, and also this one and this one. So again, single, this is 2, apply, and the direction is wrong, so I'm going to flip the direction of the mesh, apply, OK, and assign this one to this face. And as you can see, now I have more dense mesh around those areas. Okay, so as you can see, you will have more control over your mesh when you apply when you partition your face. You can also do this one for on 3D. So as you can see, these are basically geometry that you can actually apply a structure mesh, and similar to the previous one, these are the one that you can now when you have a hole, when you have an isolated face, isolated edges or vertices. So these are the ones that you cannot apply a structure mesh. Okay, so now let's go to a sweep mesh. So in the next example, you're going to learn about sweep, and again the partitioning technique. So similar to structure mesh, sweep mesh has its own rule as well. For instance, if the source side contains more than one face, the angle between the face must be relatively flat, close to 180 degrees, or each face that connects the source side to the target side, a connecting side must have 4 corners, and the angle at each of the corner must be close to 90 degrees. So if you look at these two parts, if I go to mesh, you'll see that one of them is yellow and one of them is orange. Orange means that the Abaqus cannot apply mesh on that part. So if I click on a sign and select this one, click on done, you'll see that everything's off here. I cannot select any of these in hex or hex dominated. I cannot still select anything. But if I go on set, you'll see that I can apply on a structured triangle mesh on this one. On the other side, this one, I can apply a sweep mesh regardless of element shape that I select. I would be able to apply this sweep mesh. The difference between this geometry and this geometry is the only angle here. So here the angle is 45 degrees and the angle here is 43 degrees. How can you solve this? Well, obviously you cannot change your design. So one of the one way of fixing this is to apply a partition. So if I go to part, and so this is like a part 43, which is the angle there, then I can actually create a partition in this region and in this region to be able to apply a sweep mesh. So first of all, I'll create a offset plane. Selecting this one, face, enter a value. First I'll flip it, click on OK, and I know the distance from here to here is 20. And again, I'll do exactly the same thing with the other side. So I select this one, click enter value, click OK, and say 20. And then I will create a partition. So if I select this one, bring a partition, I need to select my partition, create partition, and then I select this side and use this part plane to create a partition. So I partitioned my part which had a 43 angle that I couldn't apply a mesh. And now if I go to a mesh section and go to assembly, you'll see that the structure, the part has changed the color. So Abaqus says that it also can apply a structure mesh to this region and sweep mesh to the middle. But what I want a sweep mesh everywhere. So I'll select this one. I'll select the sweep mesh everywhere, click on OK, and then what I will do, I'll just apply a element size on these ones and make it this one, and let's say 5. See how does it look like? Yeah, 5 is okay. Click on OK and assign a mesh on both geometries, and so as you can see, I have a sweep mesh on both geometries. Is it still possible to apply a structure mesh? And obviously the reason that we cannot apply a structure mesh in the mid section is because of this hole that we have there. So similar to what I showed you in 2D, you can actually partition your part similar to what you have here in 2D here in 3D, and then you would be able to apply a sweep mesh. Okay, so the next step is to talk about the unstructured mesh or free meshing. So free meshing, when to use it? When the geometry is too complex and you must apply too many partitions to create a structure. So as you can see, for instance, this is a 2D example. As you can see, if I want to apply a structure mesh, I have to apply too many partitions. I would say maybe 8 to 9, and it's possible that you won't be able even to have the fully structured part. Or when you have a 3D geometry like this one, as you can see, is complex geometry. I wouldn't say that it's impossible to apply a structure mesh, but it's going to be time consuming because you have to create too many partition to apply a structure mesh. So this is the time we use a free meshing. Free meshing with a quadrilateral element is a default meshing technique for two-dimensional region. The free meshing technique with a quadrilateral element can be applied to any planar or curved surface. You can use this technique to mesh a region with a tri-quad or quad dominated element for a two-dimensional and three-dimensional region. The last thing I want to show you here in mesh control is the algorithm that we have for free or unstructured mesh. So we have a medial axis and advancing front. The medial axis algorithm first decomposes the region to be meshed into a group of simpler regions. The algorithm then uses a structured mesh technique to fill each simple region with the element. The advancing front algorithm generates a quadrilateral element at the boundaries of the region and continue to generate a quadrilateral element as it moves systematically to the interior of the region. The question is which one is better? I really don't know myself. So you must experiment with two algorithms to obtain optimal mesh. So no one can tell you which one is better. It's basically really depends on the geometry, and you must try both algorithms to see which one will give you an optimal mesh. However, there are some guidance. For instance, if the region being meshed is relatively simple and contain many elements, the medial axis algorithm generates a mesh faster than advancing front algorithm. The element produced by the advancing front algorithm follow your seeds. Then the resulting mesh may include some skew in the element in a narrow region. So as you can see here in this example, if I make this one bigger, you'll see that I have some skewed element, which we generally try to avoid this type of thing. So as you can see, this is a medial axis. So I have a nice mesh in this edge, but in advancing front, there are some skew one. And the advancing front algorithm may generate elements of more uniform size with a more consistent aspect ratio. So if you look at this example, you'll see that when the geometry is like this, the advancing front will provide a more consistent and uniform size element in comparison to medial axis. So as you can see, we have three different geometries, and depending on the geometry, one of these algorithms are more suitable. And so that's why, as I said, it's very difficult to say which technique is the best, but generally I recommend you to start with a medial axis as a default option, and then you can change it to advancing front to see that if you'll get any better results. Okay, so we are done with this one, and now we're gonna move to the last part of this video, which is basically element type assignment that you're gonna learn in this section. So now in element type, here as you can see, when you click on assign element type, we have a new menu here that you need to select the element library, geometric order, the family, and the type of element that you have if you selected quad or tri. So let's start with this one. So as you can see here, we have standard and we have explicit. So standard, and this goes back to basically what you have selected as a solver. So if we have in the solver here, when we create a solver, we have different options. So if you select anything except explicit, dynamic explicit or dynamic temperature explicit, then you're good to carry on with a standard. And if you're selecting the explicit one, then obviously you have to change the element library to the explicit. So this section will basically depends on the step or the type of the simulation that you're going to run. Is it explicit or dynamic, or is it static? Okay. So I just need to go here. So when you change this one, you'll see that the menu will change at the bottom section. So when you have an explicit and a standard, so you see that some of these items will change. The next step is the family. So the family basically here will show you, you have to select the element type. And if I select this one, you will see that the name of the element at the bottom will change it. So for instance, in the plain strain, I have CPE4R, a four node bilinear plane strain quadrilateral reduced integration hourglass control. If I go to plane stress is CPS4R. So these are the name of the elements that we have in Abaqus. So when to use these plane stress and plane plane strain and plane stress. In 2D we have different item under family, but what you're going to use in this course is plane strain and plane stress. When you created your part in 2D planar and deformable or discrete rigid, and when it's in shell. Okay, so when you're in 2D and shell, you have to use plane strain and plane stress. So which one is the best? Again, this depends on your geometry, so I cannot really tell you you definitely use plane stress or definitely you have to use plane stress. There are some guidance, but you have to check your geometry before selecting the plane stress or plane strain. Plane stress element used when thickness is small relative to in-plane dimension. So let's just look at this one. So what we have here, the thickness is much smaller than in-plane dimension. The stresses are a function of the planar coordinate alone, and out of plane normal and shear stress are equal to 0. Plane strain element used to replace a thick plate or section. So as you can see, when you have a very thick plate, then that's the time we use a plane strain. Strain are a function of the planar coordinate alone. So what we have here, we consider the strain along z-axis to be 0. But in plane stress, we consider a stress to be 0 along z-axis. And the strain is not 0. And here is opposite. So we consider the strain to be 0 and the stress has a value. And out of plane, normal and shear strain are equal to 0. So also we have beam at the top here, beam section, and this is the one that we have to use for a wire. So if I go to the wireframe example and change this one to assembly and select assign element type, select this one, you'll see that the stuff that we have at the top has changed. So we don't have any more plane strain. The only thing is available is basically a beam section which is the element number is B21. It's a 2 node linear beam in a plane, and also we have truss as well, which is T2 D2, a 2D node linear 2D truss. So you can choose either of these based on what you have selected in the material. So if I go for beam, that means that in the property section, when I created my section, I selected the beam rather than truss. So this is very important. The third one that is you're going to learn about the 3D shell element. So when you go to 3D shell plate, and if you go to mesh assembly and then select this one, and then you'll see that again here I have some new items. Again, we're not going to use the other one, which is because they're more therefore a more complex analysis. The only one that we're going to use here is a shell, and you have to use shell when you make your geometry in 3D deformable shell and either of these type. And the element type is going to be S4R, a 4-node doubly curved thin or thick shell with a reduced integration, hourglass control, and fine-node members strain. Okay, so the next one is going to be a solid. So solid is when you have basically 3D deformable and is made in solid. And we can see that in mesh control here. So this is solid structure, and if I click on this one, I have to go to part, select this one. So as you can see here, I have 3D stress. So this is the one that is on the default. So when I have a 3D model, I have to use this one, or I have to use continuum share or continuum solid share. So when do I have to use this one? If you remember from composite that you learned in the property section, we could actually create a 3D element which behave like a 2D. And that's the time we call them continuum share, and you learn about it in the property section. And we use these one when we actually make a composite. We want to simulate a composite. And if you remember, we could create these one using a continuum shell. So when you create a continuum shell element, then from here, you have to select a continuum shell. If you select the solid, then 3D stress, then you will get an error that the wrong element has been chosen. And also I've explained this one already, that it's about a beam truss. So now we go back to the first order or second order. If you remember here in the picture I showed you, some of the elements had 2 nodes, some of them had 3 nodes. And this is the one that basically there's integration points. It's the point that the software will solve the mathematical equation for each of these nodes. And we have an extra point here in the middle. So let's just select, for instance, on this one, you see that here we have a geometric order, we have linear, or we have quadratic, okay? Geometric order describes whether your element contain only a corner nodes, which is a first order, like this one, so you have only on the corner, or if they contain a corner node and mid-side node and second order. So you have a second order here, as you can see, or we had these this graph here as well, so that you can see the first order and second order for 1-dimensional, 2-dimensional, and 3-dimensional. So this is the way that you decide to go for 1-dimensional, first order or second order. And what would be the difference? First order is computationally more efficient and is better for a contact convergence. However, the second order elements are more accurate in deformation, better geometric representation, especially when you have curves. As you can see here, this is a very good example. So you see that because I don't have the element or node in the middle, you see that I don't have a really nice and smooth curvature. However, this side is the second order, and as you can see, the curvature is much smoother. So when you have a complex curve, then definitely it's better to use a quadratic, because you will have a smoother curvature and that will increase the accuracy. However, that comes with a cost because it's computationally more expensive. So then you have to basically balance your model. So you need to think about, if you're actually adding a quadratic geometric order, are you going to get more accuracy, or do you really need the accuracy? So these are the questions you need to ask yourself before choosing a linear or quadratic. The next step is to select the type of element that you have, and you select these one based on what you have selected in the mesh control. So as you can say, hex dominated, tet, or wedge, and that's basically the way that you select these one. And then we have at the bottom we have some hybrid formulation, reduced integration, and incompatible mode. And these will change based on a 2D or 3D simulations. As you can see, in 2D we have only reduced integration and incompatible mode, and in 3D we have hybrid formulation, reduced integration, and incompatible mode. And if I go to quadratic, you will see that I only have a hybrid formulation and reduced integration. So let's start with reduced integration. Reduced integration uses a lesser number of Gaussian coordinates when solving the integral. Clearly, the more Gaussian coordinates you have for each element, the more accurate your answer will be. But this has to be weighed up against the cost of computation time. The expression full integration refers to a number of the Gaussian points required to integrate the polynomial term in an element stiffness matrix exactly when the element has a regular shape. So as you can see, in the linear we have 4 points, and the quadratic we have 9 points. But however, the reduced integration uses fewer integration points in each direction than the fully integrated element. And as you can see, we have a single integration point for a linear, and we have 4 of them for quadratic. And then we have a hybrid element, so you can activate this one. Hybrid element are used when the material behavior is incomparable. Poisson ratio equals to 0.5 or very close to incomparable when Poisson ratio is above 0.475. Rubber is an example of a material or flexible adhesive with an incomparable material behavior. And incompatible mode element available only in Abaqus standard or an attempt to overcome of a problem of shear locking in fully integrated first order element, as you can see here. So when we have linear, we don't have this one, we can activate the incompatible mode. Since shear locking is caused by the inability of the element's displacement field to model the kinematic associated with the bending, additional degree of freedom which enhance the element deformation gradient are introduced in the first order element. So these are kind of like for complex examples that when you try to solve a problem, you suddenly get an error and related to mesh. So basically, majority of the convergence error that you can come here, activate this one to see that if that can solve the problem. So this is the end of this tutorial. I hope you learned about mesh and enjoyed this video. If you have any question, please let me know. Thank you.